All right, team. Welcome back to the Unit 4 lecture video series. Today we're going to be going through the Unit 4 Day 4 notes, continuing our applications of derivatives journey. Okay, so the first application we looked at was a real-world one. We looked at related rates, moving parts, finding the derivative there. And then last class, we started going into the theoretical world and looking at a theorem called the extreme value theorem, which says if a function is continuous on a closed domain, then we can guarantee the fact that that function is going to have an absolute max and an absolute min. Now, again, that theorem does not guarantee where that happens, just that it has to happen. Today, we're going to continue on our theoretical journeys, and we're going to be looking at another theorem. It's called the mean value theorem, or what we call MVT for short. So we're going to learn what is the mean value theorem, what does it guarantee, and then how can we use that theorem. Okay, so to get your brain going, here's what I want you to do. If you're looking at the notes packet and following along, there are 8 graphs in this section, okay? 6 on the first page and 2 on the back page. And then for each of these graphs, here's what I want you to do. You're gonna pause me, okay? And you're gonna draw the secant line that connects the 2 endpoints of the graph. So that's step 1. Step 2 is I want you to draw a tangent line, if it exists, that would be parallel to the secant line drawn in part A, and then estimate the x-coordinate of that tangent line. So I'll go ahead and we'll do one together, and then I want you to pause me and try the rest. So I'm going to go ahead and draw the tangent line, and I'm going to cheat and totally use a line, okay? I'm going to draw a tangent line I'm draw the secant line through the 2 endpoints. So that would be the secant line. Then what I want to do is I want to figure out, is there a tangent line that would be parallel to it? So using my technology, what I'm going to do is I'm just going to kind of drag a parallel line and estimate, okay, it looks like maybe right there, the tangent line would be parallel to the secant line. And then I'm going to say x is approximately 2. Okay, so go ahead and pause me. Try these 7 remaining problems, draw the secant line, figure out are there any tangents that are parallel to it, and estimate the x-coordinate of that point of tangency. Okay, so you should have gone through and done all of the ones on your own. So let's just kind of quickly see what did we come up with. So I'm going to go ahead and undo whatever I just did. Okay, I'm going to go ahead and draw that secant line, and then I'm going to clone it, and I'm going to find parallel tangents. So I have a parallel tangent right there, and a parallel tangent right there. So hopefully you discovered that there were 2 for this one. So I'm going to estimate those 2 points to be at about negative 0.5 and maybe 3. Okay, so let's go ahead and do this next one. Here's my secant line. I'm going to try to find a parallel tangent to that. So maybe I go down. Ooh, that's not a place where I can have a tangent line because there's a corner there. So let me go up and see. Oh, it looks like there's one right about there. Okay, and that looks like it's at about x equals, I'm going to say negative 0.5 again. It might be more like 4.6-ish, but again, as long as you're close. Okay, let's try this next one. I'm going to draw the line through the 2 endpoints for the secant line, and then I'm going to try to see, is there one that is a parallel tangent to that? Let's see, let's clone this line. So if I slide it, no parallel tangents. That's impossible because there's a jump. So there's actually none here. So this one is no, my gosh, guys. No tangent that's parallel. Okay. Let's look at 5 and 6. So let's go 5. Here's my secant line. And let's try to find a parallel tangent to that. Let me clone it. That's me cheating because that gives me a parallel line, and I'm just going to slide that line. Is there any point where the line would be tangent? Now, that's an interesting point, but that point actually, the slope doesn't exist. There wouldn't be no tangent line because there's a corner. So that one actually doesn't have any. So I'm going to say no tangent. Okay. Now, let's do this one. All right, got my parallel. Ooh, this one's nice because it's kind of flat. It's a horizontal. So if I want to clone this one, again, that point doesn't work because there's a corner, but there is a point right there. So I'm going to estimate that point to be at about x equals 0. All right, last two to try, and then we're going to do some analysis of this. So here I got that. I'm going to clone it. Let's see. Oh, yeah, it looks like there's one right about there. And maybe right about there, right before the jump, because the jump, it looks like the slope would be approaching 0, but maybe right before it. So let's say like right there and maybe right there. So x is approximately 1.1 and negative 0.2. Okay, again, I'm estimating. They don't have to be perfect. I'm just kind of thinking where would I have that slope? Okay, and then finally for number 8, here's my line. If I drag that, if I were to clone that line, I would have no point of tangency here. Okay, so now what I want you to do is I want you to look at your 8 graphs holistically, and I want you to answer question 9. So go ahead and pause me for a second, and I want you to look at question 9. Some of these had parallel tangents, some of them didn't. Where did those parallel tangents happen? Okay, and then look at the properties of them. So go ahead and pause me. Okay, welcome back. So for which graphs were you able to draw at least one tangent line? So I was able to draw one for graph 1, graph 2, graph 3, graph 6, and graph 7. Which of those graphs that listed were continuous? Okay, so 7 wasn't continuous, but I could still do it. 6 was continuous. 3 was continuous. 2 was continuous, and 1 was continuous. Which of those graphs were differentiable the whole time? Ooh, well, that one is just graphs 1 and graph 2. So which characteristic, continuity or differentiability, guarantees that I can draw at least one tangent line? So let me look at the ones I couldn't were 4, 5, and 8. So if I look at 4, discontinuous, 5 is continuous but not differentiable, and 8 is discontinuous. So if I had to say which could I guarantee, well, there were graphs that were discontinuous where I could still draw one. But if I wanted to guarantee, were there any graphs that were differentiable that I wasn't able to draw one out? And the answer to that is no. So if I wanted to guarantee that I could draw a parallel tangent, I would need to guarantee that differentiability occurs. There was no, if you look at these pictures, there were places where it was continuous, but I didn't have a parallel tangent, like question or graph number 5. If you look at graph number 5, that graph is continuous, but there was no parallel tangent. So even though a function is continuous, that's not enough to guarantee a parallel tangent. Whereas if I look at graphs 1 and 2, those graphs were differentiable. There's no way I can't have one. Okay, welcome to the mean value theorem. So now let's kind of look at what this means. In general, for a function on a closed interval, a to b, if we have a tangent line that is parallel to the secant line, then the equation of that tangent line at c, so let's say I want the tangent line at x equals c, and I know it's parallel to the secant line. Well, what do I know about parallel lines? They would have the same slope. So if the secant slope would be f of b minus f of a over b minus a, then the equation of my tangent line would be y minus f of c equals f of b minus f of a over b minus a times x minus c. Okay, so if I know it's parallel, then if I find the AROC would be the same thing as the tangent, as the derivative of the IROC there. And I could use either. Okay, let's look at a different example. At 1 o'clock, Alexis picked up a fare card at the entranceway of a tollway. At 2:15, she pulled up to a toll booth 100 miles down the road. After computing how much Alexis owed, the toll booth operator issued her a speeding ticket. Alexis claimed she hadn't been speeding. Was she lying? So go ahead and pause me and ponder this question. Does she deserve a speeding ticket? Yes or no? And what could you say that would guarantee the fact that you know for sure that she was either speeding or not speeding? Okay. So you probably pondered it, and hopefully you discovered that if she went 100 miles in an hour and 15 minutes, so 1.25 hours, that averages 80 miles per hour. Okay. That is her average rate of change. There is no way that she couldn't have averaged 80 without going 80 at least once. And that's because distance, if we talk about distance is a differentiable function. I can't jump speeds, guys. It's a differentiable function. It's continuous and differentiable. And since her AROC is 80, we have to hit an actual value of 80 at least once. Okay. So since we can guarantee that she had to go 80 at least at some point, we would have to give her a ticket. So Alexis is a big fat liar, in other words. Okay, so my loves, that is the mean value theorem. Okay, the mean value theorem, or what we call MVT for short, is the guaranteeing slope theorem. So I like to call this the guaranteed slope theorem. Okay, so what the hypothesis is, if a function is continuous on a closed domain, so I'm going to say on A to B brackets, and differentiable on the open interval A to B, because we don't talk about slope at endpoints. That's confusing for everybody. Okay. Then here is what we can conclude. Here is the guarantee. The mean value theorem connects the average rate of change of function with the instantaneous rate of the same function in the same interval. The theorem says that in that function, I can guarantee that there is some point that has a slope equal to whatever the slope of the endpoints is. There has to be a parallel tangent. The one slope I can guarantee has to happen at some point within that interval is whatever the AROC is. There has to be an IROC equal to the AROC. Okay. Then, so let's write this. Then there exists, ooh, look at that fancy math language, at least one C, where C is between A and B, where f prime of C equals f of B minus f of A over B minus A. Okay. Now, again, let's talk about what this is guaranteeing. They're saying there is one slope in a function that I can guarantee as long as that function is differentiable. And the one guaranteed slope I'd have to have at some point is whatever the average rate of change is. So whatever the average rate of change is of that function, there has to be a point within that interval that has the same slope. So there has to be a tangent line that is parallel to the secant line. Okay, that has to happen if the function is differentiable. There's no ifs, ands, or buts about it. The theorem only tells us that there has to be that number. It does not tell us how to find that number. Okay, so we are going to look at like what can we guarantee? Does mean value theorem apply? And then let's go a step further and actually find where this happens. Okay, so first I want you to look at these 4 graphs because I can count. Does mean value theorem apply to these functions? Yes or no? So pause me, think about it, and then unpause me. Okay, so let's go over it. Question for the first graph is no. Why not? Not differentiable. B, does it apply? Yes, it's continuous and differentiable. This is a no, not continuous. This is a no, not closed, not differentiable. Okay, now, here's the hard part. Even if it does not apply, could it still happen? Yes, there were graphs in 1 through 8 that were discontinuous and not differentiable that had parallel tangents. The mean value theorem doesn't talk about those. It talks about when can I guarantee it. So this one, I can guarantee it has to happen. Whereas this one, I can't even draw a secant line. So I'm just like, can't even on that one, but it could still happen. It's just not a guarantee. Okay, so we're going to talk about the guarantee of mean value theorem. Okay, so let's try some problems dealing with mean value theorem. Show that f of x equals x squared plus 2x minus 8 satisfies the hypothesis of the mean value theorem on 0 to 2. Then find a solution C where that would happen, where the IROC would equal the AROC. So this is the conclusion of the mean value theorem. There has to be a tangent line that has the same slope as the AROC, or the slope of the secant line. Okay, there has to be an IROC that equals an AROC. So let's see if we satisfy. So let's check. Is it continuous on A to B, on 0 to 2? Well, yes, it's a parabola. Is it differentiable on open 0 to 2? Let's check it. Okay, if it was differentiable, the derivative would have to exist. So if I find the derivative here, I get 2x plus 2. Is that derivative continuous? Yes. Does that mean f of x is differentiable? Yes. Okay, there's no corners or cusps or vertical tangents in this. So is the hypothesis satisfied? Yes. F of x is continuous on 0 to 2 closed and differentiable on 0 to 2 open. Okay, since the hypothesis is satisfied, we know the conclusion has to be true. We know we can guarantee an IROC equal to the AROC. So what we want to do is figure out where, and the theorem doesn't tell us that. We're going to have to do some work. So let's think about it. If I find the slope from 0 to 2, so let's find the AROC of this function between 0 and 2. So if I plug in 2 into our function, we get, let's see, 2 plus 2 squared plus 4 minus 8 minus 0 plus 0 minus 8 over 2. That's going to give me 4 plus 4 is 8 minus 8 is 0 minus negative 8 is 8 over 2 is 4. Okay, so I get an AROC equal to 4. So the one slope I know has to happen in this interval is a slope of 4. So if I want to figure out where the function has a slope of 4, I'm going to set my slope function, aka my derivative, equal to 4 to figure out what x gives me that. And so if I set my derivative equal to 4 and solve that, I get x equals 1. Now, is x equal 1 between 0 and 2? You better believe it should be. Okay, so did we find where it happens? Yes. So we found the AROC and then set f prime of x equal to the AROC to locate what x coordinate we have. So at x equals 1, f prime of x equals 4. Okay, and 4, again, is the AROC of the situation. Now again, if the hypothesis isn't satisfied, could it still happen? Yes, it still could, but we just can't guarantee it, okay? There are actually a lot of things like the mean value theorem that we can conclude based on our derivative function. Okay, so we can conclude based on the derivative function where we have a parallel tangent to the secant. So we could find that using the derivative function. Last class, we were looking at what happens when extreme value theorem does not apply and we're trying to find local mins and maxes. We discovered there that the derivative function also gave us information to help us figure out that question, whether we did it. And we looked at that by looking at what the slope is. So if you remember from our best friend, the chart, okay, if I wanted to talk about f of x increasing, first of all, let's define f of x increasing. F is increasing if any x that comes before another, its height is less than the height of the second x. The first x is lower than the second x. Okay, that's the definition of increasing from Math 4. If x1 decreasing means if I have a left x and then a right x, the left x is higher than the right x. Okay, so those are the definitions of increasing and decreasing. And we call these graphs like anything that's strictly increasing means it's just increasing, and strictly decreasing, we call those types of functions monotonic, like single behavior. Okay, here's a corollary statement we can conclude based on this definition. And this is what we did in our chart. 1. If f prime of x is greater than 0, f of x is increasing. It's coming back a little bit, I hope. And 2, if f prime of x is less than 0, f of x is decreasing. Okay. So now what I can do is I can find values algebraically, but before we could only do this graphically given the derivative, but now that we have all our rules together, we can actually figure out on what intervals a function is increasing and decreasing based off the derivative function itself. So if I wanted to find the extreme values of a function and the intervals where the function is increasing and decreasing, I could use the derivative function to give me that information. And so I would find the derivative function here, okay? And then what I would do is I would figure out where are my critical points. This is what we did last time, and I would get that critical point. Then you have a couple of options. You can graph the derivative graph, okay, and figure out where it's positive, where it's negative. So I can see if I graph the derivative function 2x minus 1, I know it's on the negative side from negative infinity to 1/2, and on the positive side from 1/2 to infinity, which means my function decreases and then increases. You can also do that using a sign chart. Okay, so if I have f prime here, and I plug in a number less than 1/2, like 0, I get a negative value out of the derivative. If I plug in to the derivative something greater than 1/2, like 10, I get a positive. Okay, so I know f of x is decreasing from negative infinity to 1/2 because f prime of x is on the negative side or is less than 0. F of x increases from 1/2 to infinity because f prime of x is greater than 0. Okay, now what does that mean is happening at 1/2? If I go from the negative side to the positive side, this is a local min. So we have a min of, let's find it, f of 1/2. 1/2 squared minus 1/2 minus 12. That's 1/4 minus 12.5, negative 12.25. So min of negative 12.25 at x equals 1/2. You're probably like, Ms. Bowman, that was super fast decimal work. You betcha. Okay, let's try another one. Find all extreme values of this function in the intervals where the function is increasing and decreasing. Okay, so a little bit different type of function, but we can still use the derivative function to help us analyze what f of x is doing. Okay, so if I find the derivative here, it'd be e to the u is e to the u times du, which is just negative 0.5 e to the negative 0.5x. Now, if I set that equal to 0, and I divide both sides by that negative 0.5, I end up with this statement, which actually, guys, the e function is never going to hit 0. This has no critical points. Well, what does that tell me? That tells me the function is always increasing or always decreasing. There is no extrema, no extreme values. Okay, well, let's see by testing the derivative then what's happening. If I plug in a number into my derivative function, any number I want, like 0, I end up with a negative. What does that tell me my function is doing? Well, my function is decreasing from negative infinity to infinity because f prime of x is always negative. It's strictly decreasing. And if you know this graph, you know it looks like this. Okay, you could have answered that question without calculus, but it's always good. Okay, what else can the derivative function do? Since we're doing derivative functions, it helps us figure out mean value theorem, it helps us figure out increasing, decreasing, and maxes and mins. It will also help us find antiderivatives. Now you're like, oh my God, what just happened here? Did she just say the word antiderivative? I did. Okay, let me explain what the antiderivative is. Find the derivative of each of these. Pause me and take 30 seconds. Find the derivative of each. F prime of x here is 2x. G prime of x is 2x. F prime of x here is 9x squared minus 5. G prime of x here is 9x squared minus 5. What do you notice about these derivatives? Okay. Some of them are the same, you're right. Were the functions the same? No, they were different. How are they different? Ooh, good point. They were different by their constant. Okay, so here are some takeaways. Some functions have the same derivative. They vary by a constant. Okay. So now you're like, well, what, Miss Mummy, you didn't tell me what an antiderivative is. Okay. Guys, an antiderivative is if I give you the derivative, could you tell me the original function? So an antiderivative is finding the original function from a derivative, from f prime. Okay, so let's look on the next page. Find all functions f that have the following derivatives. Now, an antiderivative, if I give you a derivative function, the antiderivative is what is the OG? What would that function started as? So if I give you the derivative 2, you're thinking, what was the original function? You're going backwards, team. And if I tell you the derivative is 2, then you know the original function had to be 2x, but based off what we did, we know that there are lots of different things that we could have here. So we know there could be a constant, and those constants can be different. And so I'm just going to say 2x plus some constant. So every function, multiple functions have the same derivative. So if we're going backwards, we know that those functions are always going to vary just by their constant. So we just put a little plus c to represent all the different constants that we could have. All right, so if f prime of x equals sine of x, let's find the antiderivative. Whose derivative would be sine? Now, if you said negative cosine x, kudos to you, because the derivative of cosine is negative sine, but if I made the cosine negative, then it would cancel out to give me positive sine. Okay, now the question is, what would I need in order to figure out what the constant is? Well, not only would I need the derivative, but I would also need to know a point on the original function. If I had a point on the original function, then I could figure out what the actual antiderivative particularly would be. So let's think about this one. Ooh, this one is tough. They do give me a point, so I'm going to be able to find c. So we're going to use this to find c, but I have to go backwards from this derivative. Pause me and try it. Okay, now let's see what you came up with. What I'm going to do first is I'm going to put this into a calculus-friendly form. So I've got to think to myself, okay, I know that the function would have been a power rule. And I would have had to bring the exponent to the front and decrease it by 1. So I'm going to go backwards here, and I'm going to figure out what the original exponent would have to be. And I know if I add 1, that's like going backwards, that would be 1/4. And the fact that there's a 1/4 in front means that there was no other coefficient there, that it just had to be x to the 1/4. How could I check myself, team? Just take the derivative, okay? Plus c. Now what I would do is I'm going to use this point to find my c. So I know when I plug in 1 for x, I should get out -2 for the output. So I have -2 equals 1 plus c. So c equals -3. Therefore, my function, my antiderivative, would be x to the 1/4 minus 3. So that function has a derivative equal to the one above, and it goes through the point 1, -2. All right, try the next one. When you're ready, unpause me, and we'll go through the solution. Okay, so if my derivative is 2x plus 1 minus cosine x, I'm going to work backwards. Whose derivative is 2x? X squared. Whose derivative is 1? X. Whose derivative is negative cosine? Negative sine. Let's check it. Derivative of x squared, 2x. Derivative of x, 1. Derivative of, actually this should be positive. See, let's see, derivative of sine is cosine, so I have to keep it negative. See, I had to double check myself there. Plus c. Could have a constant, have to have a c. C stands for credit, guys. No c, no credit for antiderivatives. Now I know if I plug in 0, I'm going to get out 3. So I'm going to set it equal to 3, and everywhere I see x, I'm going to plug in 0. I'm going to be careful for these trig functions because they're not always 0. But this one is. I get c equals 3. Therefore, f of x equals x squared plus x minus sine x plus 3, and you found the antiderivative. Okay, let's try one more. How can the derivative, now that we've done antiderivatives, we've done increasing, decreasing, we've done like mean value theorem with derivative functions, what else could the derivative functions help us find? This is one the AP exam loves. For what value of k will this function have a relative maximum at x equals 2? So the reason why they ask this question is they want you to think, what does it mean when a function has a relative maximum? Well, it means the function is going to look like this, and at that relative maximum, the slope is 0. So I'm going to use that point, that fact that I know the slope is 0, to figure out what k needs to be. So if I have my function here, and I'm going to go ahead and bring that x out, and I take the derivative, I know that if I plug in -2 into this function, I should get out 0. So I'm going to write this as 1 minus k over x squared. So I know I'm going to set that derivative equal to 0, and I'm going to plug in -2 for x, and I'm going to figure out what k needs to be. So if I solve this equation, I get k over 4 equals 1, so k equals 4. Okay, so just different applications of the derivative function and where we could use it. We're going to build on this in the next lesson, but that's all I got for you today, so enjoy.